So hello, everyone. For those of you who could make it here in person today, thanks for joining. In today's webinar, we're going to be discussing some of the introductory concepts around segment routing. Leading the discussion today is Jeff Tantsura and Nick Buraglio. So without any further delay, I'm going to hand it off to them.
Hi, I'm Nick Buraglio. Been a network engineer, architect, and security engineer for about 24 years. Primarily work in the service provider space, but I've got experience in research and campus as well.
Jeff Tantsura, I've been networking space probably about the same amount of time, both service provider as well as vendor. With regards to segment routing, I did all of its standardization starting from early days. So pretty much designed first implementation of segment routing on Redback Ericsson routers, as well as tested in Berlin the first implementation of Cisco, and back then, I don't remember who else, Nokia probably. Juniper didn't have implementation yet, so let me admit someone. So the idea here, I have some reasonably old slides. They're just high level to lead the discussion. It's really about what we see today. Nick spent a lot of time testing the stuff. I haven't touched segment routing for the last 3 years in terms of really on the router. So we will try to pinpoint between what standards do versus what real routers do and experiences. Please do ask questions. Let me share the slides and we'll start from there. So this discussion is pretty much dedicated to SR and PLS. You are more than welcome to ask questions about SRv6 and what's going on. We're not covering it here. It's still kind of very poisonous discussion, and vendors have very different opinions what it should look like. I would really recommend if you read segment routing discussion Nanoc 2 weeks ago, so you'll get kind of feeling of what people think about it. Let's see. So this is pretty much the agenda for today. Again, we are not going to strictly follow slides or rules or anything. It just wasn't the slides. So you might often hear that Cisco invented segment routing. Not true. In Redback networks in 2004, actually we filed patent in 2003. The proposal was really to do segment routing with LDP. And there is patent and it's actually disclosed with regards to the RFC. So the first idea about source routing within PLS was conceived in Redback, and actually we presented an ITF in 2004, and back then Yahav Rector and Eric Rosen said, no way, which was kind of killed. So it came back in around 2012, Cisco filed probably about 50 patents on it. And back then, Clarence started to reach out to all other people and build fantastic ecosystem of vendors. We will all work together. And it resulted really in implementations that interoperable. We'll talk about indices versus absolute values and how it came up. So in 2014, we started a working group called Spring in ATF. And in 2017, we started to see first deployment. As of today, it's really mainstream technology. If you deploy in PLS today, probably you are not doing LDP. Some people still do RSVP. There are reasons to do this, but most people are really looking into SR. So what is segment routing? It really leverages the source routing paradigm. So you define the path packet as taken throughout the network at the ingress point of the network. You are not leaving the tunnel like you're not leaving the tunnel when you enter with your car. You only leave in the tunnel at the end of the tunnel. And in case of SR and PLS, we have a bunch of seats that are stacked in the same way as labels do. And they're actually, in forward implementations, there are labels. And you use one of them at the time to forward packet. You might have more than one packet and use them not only for forwarding, but as an instructional set. You can also look up one seat in context of another. So RC5331 actually give you ability to use them as context labels. Juniper is well known for using these technologies.
So real quick, Jeff, from the practical perspective, Jeff mentioned that folks that are deploying an MPLS network today are probably not going to use LDP, but they may still use RSVP, although the most of the things you can do with RSVP are available and simplified in segment routing. And one of the things that's kind of important to understand is that a big reason for going down this path rather than the traditional LDP, RSVP path is that it simplifies the complexity of each device in the path. So as Jeff mentioned, you push a label in at the very beginning. So it's considered quote unquote source routing. And then that has knowledge of the entire path. Whereas the legacy protocols in general, especially in RSVP TE, you're configuring every single device along the path. So not only does redundancy become more complex, just simple functions of doing traffic engineering are far more complicated in the older mechanism. So that's a really big reason that a lot of folks are looking at this type of technology today and going forward.
As we go through SDN use case, we'll discuss why would you do one versus another. And as you know, pendulum always goes through complete removal of state to complete statefulness. And truth is usually somewhere in between. So you lose a lot of visibility and ability to do things when you lose the state, but hey, you gain simplicity. So choose your poison. So how it works when you configure your device to do SR, it will advertise capability. Hey, I'm SR capable. As you know, segment routing requires link state protocol to work. Or BGP, but it's a completely different thing, right? So in general, you would say, I'm a router, I support segment routing. This is my SRGB. And so the interesting point is about SRGB in 2013, when we started testing, all vendors besides probably OSXR back then had fixed H or header file that had label range for LTVP and label range for SVP, label range for LDP. So we connected all routers together, and guess what? Nothing worked. So we figured out it will take us years to configure dynamic label allocation, which by now is the case 7 years later. Back then, we decided to go with indexes. What it really means, you have your SRGB as supported by your hardware or as defined your header file, but you're using index to it, so your neighbor doesn't have to support same SRGB. Even so, it's best practice to use same SRGB across the network. And there are reasons for that. It's not required. You could use indexes instead. So you advertise base value plus offset rather than the real value.
And one of the important things to understand here is that the SRGB is the global block of labels that's used within a network. And there's a little bit of a misnomer in the terminology that was confusing to me at the beginning because it's considered globally unique, or it's called globally unique. So being a service provider focused person, the first thing I thought of was, it's like PI address space, or I have to get it from somebody. But all it really means is that it's unique within your enclosed ecosystem. So you don't really reuse labels like you can. Everything is carved out and very well defined, which makes it a little bit easier to control and see what's happening when you need to troubleshoot it.
And SRGB is a configurable block. So usually you would go in something like router, segment routing, and say my SRGB is 10,000 to 20,000. And again, it could be different on every router. The fact that there's interaction between the indices and the actual block of labels that's instantiated in FIP gives this ability. And this is one of the best examples how multi-vendor communities solve this issue.
Yeah, and one thing that's pro tip here that I had to figure out the hard way is that if you're doing a multi-vendor environment, there may be constraints per platform of what they expect that SRGB to be. So one vendor may have, 20,000 through 30,000, and one vendor may have 60,000 through whatever, and they have to match. Like, you have to have that consistent across your entire segment routed backbone or area. So you have to find whatever the overlap is if you're doing a multi-vendor environment. And a lot of times this stuff is fairly well documented in your getting started guides or your configuration guides, but just be aware that in a multi-vendor environment, you need to make sure that those all match, and they likely won't by default.
And so kind of to provide more details here, if you are just doing basic forwarding, they don't really have to match. When you go into more interesting use cases such as anycast, such as really extensive traffic engineering, this is where different SRGBs might become problematic, especially if you use centralized controller, you signal the label, someone has to resolve them, then it becomes complex. But practically, if you just need to forward traffic, you could have different SRGB on every device. This is the whole idea of the index. So the common cases or common seed types in SRMPLS are prefix seed, assigned out of SRGB, must be unique with the routing domain. Two most common use cases is to advertise a prefix or be nodal seed. So we are going to see now the encoding, and it has N flag. When this flag is set, the seed becomes nodal seed, so it identifies the node. Usually it's a loopback. Nodal seed must be a host prefix, so /32 or /128. And adjacency seed, usually locally significant, usually allocated on configuration, is meant for traffic engineering. So when you need to override default forwarding behavior, which is really shortest path, you would say, follow this adjacency seed, which identifies uniquely, unidirectionally routing adjacency. So being OSPF or ISIS adjacency, it would use it instead of following the shortest path. So traffic engineering is completely based on adjacency seeds. Questions? So this is how prefix seed looks like. As you could see, it could be seed, or so it could be label, which is forwarding entry, or it could be index, that is control plane entry, that is the compositional index of which then label value would be created. They don't have to be the same if they are indexes. If you advertise real value, so the label here, it is the label you are going to use in forwarding. So again, you've got number of flags to tell your neighbors whether you're using indexes or labels. And when you do show this DB details, usually you would see all the details, whether it's one or another and how it looks like. So as we said, nodal seed is a prefix seed with N flag set, and this is the N flag here. So it's a configurable property, and usually you would go and say it's a nodal seed, so the flag would be set, and everybody would know this is the seed associated with the node. Adjacency seed looks somewhat similar. The only difference, it identifies not the node, but IGP adjacency. So again, we use adjacency seeds for traffic engineering, and they're not allocated from SRGB, but from SRLB. SRLB is a local block assigned to a node. It's not used for nodal prefixes. It's only used for adjacency seeds and other stuff that you might be doing locally. So if you use PC to assign some functions, you would use block from SRLB. Binding seed is a very important property. Initially wasn't considered, was actually removed from OSPF, but it's needed for mapping server. So what's mapping server? You've got LDP on one side, segment routing on another side, and you want to build an end-to-end LSP. So someone needs to take LDP binding and flat SR mappings instead. So this is what mapping server is doing. And it uses binding seeds to do so. The most important functionality of binding seed, however, is really cross-connect. So what you could do, and this is where binding seed is really used everywhere, you could take a single label and assign particular action to it. For example, it could be an RSVP LSP, it could be an optical tunnel, it could be another and segment routing tunnel. So you could stitch tunnels together. It provides an abstraction to identify a particular action on the anchor node. Very powerful concept, and again, used pretty much everywhere you see segment routing today. Nick?
Yeah, so that's one of the things that is important too when you're thinking about migration from like a Brownfield LDP network, right? It's the sort of glue that will allow you to not have a flag day of turning one off and turning the other back on more easily. I mean, there are other ways to do it, obviously, too, but it's one of the things that is often hand waved over. And there's a fair amount of documentation that's definitely worth reading on the mapping servers and different ways that it can be done. And I would recommend looking at that if you're looking at segment routing, because it's one of the things that doesn't get talked about very often.
Yeah, and it's quite complex. I mean, ISS on itself is complex given the fragmentation and all the stuff that's going around ISS and large networks. All of this kind of, you see the instantiation of ISS complexity in mappings. So if you go from LDP to SR and you're actually using mapping servers, make sure you test it properly, make sure it actually scales to your environment and you understand what it's doing to you.
I had a question about Brownfield type deployments. I know you can do it with, the mapping server to kind of interwork them, but can you run segment routing in the background like you would, if you were changing over your IGP and just make it a, less preference and then cut it when you feel like you're comfortable with what you have?
Absolutely. So this is the most common scenario. Most people don't try interwork LDP with SR, but run SR in parallel. So as you know, on router, you decide based on administrative distance which route gets actually programmed into forwarding table. So SR is no difference. Usually you would have a knob saying prefer LDP versus segment routing versus something else. So you deploy segment routing in parallel to whatever you are using. And when you feel comfortable, you just switch, you change administrative distance from one to another, as you would do with migrating from ISS to OSPF, right? You would just change preference of route on the system.
Yeah, and that's, if you go read, that's what you'll find most of the documentation on, is basically enabling SR within your IGP, typically ISIS, the one that I have the most experience with. It does also run in OSPF on some platforms. And then you essentially have a preference, and that preference gets switched. It's really not terribly different from if you're doing hop-by-hop routing and you're changing to next hop MPLS or something. Functionally, there's obviously differences there. But the mapping server allows you to do islanding, and it also would be useful in, say, a network that is a big network of acquisitions that may have different reasons for not being able to switch from one to the other. So it's a powerful stitching and transition tool.
But practically, don't do SRMS unless you really have to. It adds a lot of complexity, and not all of it is really well understood. So going in ships in the night scenario is much more common and simpler way of doing it. And again, you run two in parallel. It just, you choose preference of a protocol you prefer at particular time.
Yeah, I would say that it's one of the least, that and maybe like the binding SID, which we're going to talk about right now, are probably the two least well-documented pieces that I've found, at least when I'm doing research and labbing and prepping for actual production use.
So this is kind of use case for binding SID. Imagine you're in multi-layer network and you actually want to choose optical path on a particular device that's usually called something like optical gateway, right? Something that understands both routing and optical. So using binding seed, you could create a binding from your tunnel, which is kind of MPLS concept here, into optical domain by signaling when you hit this particular node that's anchor node that originated binding seed, and you see binding seed of value 10, then take lambda blue. So it's a very powerful concept when you need to work on multi-layer networking and when you need to signal data that's opaque to packet domain and only significant to the node where this cross-connect is finding place.
So I think that this one, you're going to go into a little bit more about this one, but a use case that is very pertinent to my particular deployment is that paths that need to be explicitly engineered over very long distance, or more correctly, many hops. You run into something Jeff's going to talk about in a minute called the label stack depth. And once you hit that limit, you can't push any more labels in and have it actually work. So the easiest way that I've found to do that is to use a PSEP controller, because you can do this all manually, but it kind of gets dicey and hard to do. But the PSEP controller will allow you to use a binding SID to say create an LSP that is 30 segments long, right? Where the label stack depth on some gear is going to range from anywhere, depending on what it is, from 6 to 18 labels deep. So using a binding SID, you can essentially stitch together LSPs using a controller.
Yeah, so we'll touch upon MSD. It's a thing that's very close to my heart, actually. I would call it my baby in a way. I have the patents and receipts on it. But yeah, so back in Ericsson, we were trying to use segment routing in radio networks, right? So we are talking about low-end Broadcom and maximum seed depth of 3-4 labels. So very soon you figure out, hey, I need 5, 6, 7, 8 labels in my label stack, but my silicon can only push 3. So what do you do? And the binding seed is really the way to configure kind of intermediate stitching points. When you reach the limitation of your MSD, you just push one label, which is binding seed. It will instantiate it as another label stack and again traverse part of the network, and then you could use another binding seed to do so.
I have a question.
Yeah.
I saw with SRv6 there was header compression as an option for combating the label stack depth exhaustion. Is there equivalent, or is binding SID now considered the better option?
No, there's no equivalent in MPLS, and I would say that MPLS encoding is very, very efficient compared to SRv6. Right? That's why people prefer to use one versus another to begin with. There's doc on the bed, let's go. So you don't really need to, you cannot compress labels. Binding SID provides this abstraction. And another nice thing about binding SID, imagine it separates two domains. So there's some instability in another domain, but as long as you can reach end of the tunnels that are identified by binding SID, you don't really care. So it stays really stable, even so you might find some changes in the underlying network. So it's really nice layer of abstraction to interconnect different domains. And MSD is becoming less and less of an issue. So it was really an issue on Trident 2 Elite platform. So really fixed to 4 labels. Linux pre-3.7, I believe, could do only 2 as well. So now if you look at something like Jericho 2, it gives you 12, 14, 16 labels depending on implementation. 3 or FP4 gives you, again, something 10 to 15 labels. So in a lot of cases, not an issue. In some cases, it is, and then you could use binding seeds to mitigate. So you signal MSD back to the controller, so PC knows exactly how deep your stack could be when it pushes back to the head-end node.
Yeah, I feel like the binding SID and the PC are really what is the secret sauce to very robust and complex traffic engineering capabilities. Those two things combined allow for some pretty magical stuff to happen.
So how stuff works really? Not that will have its loopback configured and assign a label to it or seed, in this case 20. So in LDP networks, labels are local to the device. So every device would swap one label value by another. It could be the same, but usually it's not. In segment routing specifically, we've decided to use logical function called continue. So you will be swapping same label by same label. So in this case, you'll have only single label in the stack, or if you do VPNs too. But you will always be swapping 20 by 20. So it's really continue action. You start with 20, you end up with 20, which reduces size of label stack and simplifies operations. So most vendors inside still do pop push or swap operation here, but logically you keep the same label value here. So if from a perspective it can reach that through ECMP, it will be happily ECMPing as per flow. So ECMP built in SR since day one, which is one of the biggest differences with RSVPT, and not every implementation of LDP actually does it properly as well. So it's one of very nice features of SR.
And another question here with the label depth. If I understood what you just said correctly, the label stacking problem only becomes problematic if you have if you're trying to do traffic engineering along the path, not so much if you're just trying to label switch along the way. Because if you're not doing any TE, then you're just swapping along the path. If you're doing TE, then you impose all the labels at the source router, right?
So TE is basically a forwarding concept. Imagine you're also doing some service function. So you want to signal that particular node has to do firewalling or something else. This is where you start using labels as metadata, not as forwarding instruction. And this is where your stack is starting to grow. But in general, yes, it's mostly traffic engineering. So anytime you need to deviate from shortest path, you need to override local decision. And this is where adjacency seeds come into play.
Yeah, definitely. And one of the other things is that, you kind of skirted around this, Vince. One of the use cases for SR that I've seen written about a lot is just simplification of protocol stack. So you can essentially just remove LDP by using SR to distribute your labels and never do any TE at all. It's just when you start to get into TE and then the service function chaining, and especially if you want to do explicit paths, like if you have a big network and you want to do explicit paths that always take the same route for whatever reason, then you have to start thinking about the label stack depth if you're going to exceed the number of labels you can put in a given piece of hardware.
So while we are talking about this, there are two concepts. One of them is MSD, which is really how many labels can Ingress not push when packet leaves the router, and the maximum readable depth, which has to do with ECMP and entropy. So in this case, routers advertise how many label deep can it go and read. Because as you know, in MPLS, we often use entropy labels to provide better entropy to facilitate better load sharing. So those two are kind of hardware limitations that are signaled in IGPs. MSD for the Ingress node, how many labels can I push? ERLD by pretty much every node that's going to signal how deep can you push entropy label while I can still reach it and read it, and including my hashing. So adjacency segments, as we said, they're locally to the device and instantiated in one direction as part of IGP adjacency. So in this case, even so my shortest path might go like this. If I want traffic to take path between CO, I would allocate this label here and push it into stack just below label for C. So when C receives packet with label stack on it, it will look up 9003, it will yield this adjacency, so it will take O, and then from O go to the destination. adjacency seed could be signaled as local or global. So all implementations were of doing local, but it really means that it can only be looked up on the device it's instantiated. So it must never be a top label in any case, because this device wouldn't understand it. This device wouldn't understand it. Only the device that has instantiated this label understands the meaning of 9003. You could make it global. The idea were to use it in the more kind of optical networks. But in this case, you use it exactly the same way you would use nodal seeds. So you would have label stack that is only made of adjacency seeds. There's no nodal seeds. From scale perspective, it's only instantiated and forwarding on the node C, while it's flooded through IGP to everywhere. It's just for information. No one else in this network really uses it. And this is kind of example how you would use it if your adjacency seed is global. So as you could see, your label stack here has no nodal seeds. They're only adjacency seeds. And as you go, you pop them till you reach the destination. So in some cases, it's kind of important, especially if you do OAM, you do some tracing. You don't want to allow anything. If topology changes, you don't want it suddenly to take another path because your IGP cost changed something. So you really hard code like you do in explicit ERO in RCPT. You go not 1, 2, 3, 4. 5 cannot come in between.
Right. There's a hidden gem in there too, right? So you can create this path. Say you create this path right here with your PCE, and you have an ISI SSR IGP that's carrying the labels. It has its normal IGP costing, link state information, but you want to override that for this particular path. So, you create your label stack, you understand where it's going to push it in and how it's going to direct the traffic, and you go ahead and do that, and it moves that traffic around. If that was not there for whatever reason, if the PC goes away and the LSP information gets withdrawn, the traffic it doesn't die, right? So it basically just fails over to the IGP path at that point, which may be suboptimal, right? That's why you've pushed it that direction. But at a high level, the traffic won't fail closed in that particular scenario, which is a fairly important detail that I think is something that's desirable for a lot of operators in most cases.
So what you see here is kind of continuation of what we discussed. So naive PC implementation would compute either strict path or loose path. Practically, you can compute paths that are a combination. And this is exactly what you see here. So you're trying to do traffic engineering, but you're only moving traffic from C to O. You don't need to engineer everything. And actually, your PC, when computing paths from A to C, it's taking paths that you intended. So what you could do in this case is build a label stack that is 3 label deep, because your constraints are, you need to come to node C, you need to override SPT and go to O rather than going to D, and then go to the destination. So rather than building label stack that would have A, B, C, O, P, Z, you need to provide path to C, so which is 72 in this case. You would go to C, you would take traffic engineering path to O, and then continue to that which is your destination. So this gives you ability to reduce label depth, and this is what you see in all modern PC implementations. So at least on Cisco, Juniper, and Nokia, they all do this.
So just to clarify that, then you could specify only part of the path as hard-coded, and then the rest would just take over via IGP costing.
Absolutely. So in this case, the only constraint is at some point you have to come to C. I don't really care how. And by the way, if you don't come to C, then this label becomes meaningless. Only C understands what to do with it.
right? So the 9003 is an adjacency label. It's an adjacency SID, so it's only locally significant to the router C in this case.
So what you see here is really fast. You pop 72 at C, you look up 9003, it yields path to O, you come to O, you look up 20, and then you just use IGP to 20 to Z, as Nick explained. So how do we use binding SID? So in this case, my MSD is 5, while I need 6 labels really to do traffic engineering. So what I do here, when I signal this to A, which is the heading here, so we know that label stack cannot exceed MSD. What I do is twofold. I will configure binding SID on the anchor node. In this case, it's O. I'll push binding SID at the bottom transport label. So you might still have VPN label below it, but from transport perspective, this is going to be the bottom label. So what you're going to see now, as you traverse, you come to O, and O replace 25,001, which is the binding SID, by new label stack. It's a really fib operation that says pop 25001, push 9104, 9105. And then you use traffic engineering to P, and you go to your destination. So you could build this kind of construct many times in your network, and this is what Sneak described, the best way to alleviate the kind of low-end hardware limitations.
The other thing that's nice too is on most PCE implementations, you can kind of look at the label stack that's being pushed. And if you look at the bullet point at the top, you've got binding SID is 25,001, right? Adjacency SID is 9104. And then your node SID is, 72, right? So it's really clear from the configuration of your global label space what is what, if you do it right. So it's nice and deterministic, which is one of the things that really drew me to it, because it's easy to sort of configure it in a way that makes it visually easy to help troubleshoot, which is a really big deal because troubleshooting MPLS networks is not necessarily the most straightforward thing, and the easier you can make it, the more usable it becomes. And that was a big thing for me, at least, was looking at that and saying like, oh, I can just glance at this, and as long as I configure it in a way that is sane and probably documented, I'll know exactly what each of these things are.
And remember, in segment routing, we've completely removed states from the network. So troubleshooting has become a black magic suddenly, because you have no idea where stuff is coming from. You kind of know where it goes to because you have bottom label, which is your destination. But that's all you know, right? So that's why all the discussions about how do we trace this network, how do we do accounting? I think as of today, most people decided to do accounting with net flow that signals a label, which is a hack, but there's always a price to pay for removing more specific information. The
OAM tools are getting better. But what I found is that when I want to do something complicated, when I'm looking at something like this, I typically just go to the PCE, right? Because it has topological knowledge of everything. And then, you can do PCE initiated LSPs, or you can do PCC initiated, PCE controlled LSPs, which means the controller pushes them and controls them, or automation or an operator pushes them, and then the PCE has knowledge of them.
So this is kind of how I envisioned all this stuff in 2012, and guess what? It is what it is today. All of 5G looks like this. So the beauty of combination of BGP-LS and segment routing gives you ability to stitch domains that are completely independent. And BGP gives you really good control of information. We know it's policy protocol, right? So you know exactly what you send where, how it looks like. So initial use case for BGP-LS was to talk to the controller. You can also let it being between different networks using segment routing. So it gives you the ability to stitch different domains and also expose all the capabilities, all the data, all the metadata that exists in your IGP to centralized controller to make a decision, and it goes into network slicing, whatnot, but it's foundational for right architecture to distribute what you can and centralize what you must.
Yeah, BGPLS is the thing that allows, for those that may not know, BGPLS is BGP link state. So it's essentially taking your link state database and shoving it into a BGP NLRI and then sharing that with whatever else. In most cases, it's going to be a controller, and that's how the controller gets topological knowledge of all of the links in your network. And if you couple that with things like PSEP, you can do some really interesting things and get a lot of very useful operational data out of the network and into the controller.
And distribution of information is distributed and dynamic. So you could build really large networks, and we know modern IGP scales to tens of thousands of devices. Only your computational logic, your policy enforcement is logically centralized, and this is how you scale out. I mean, we have different opinions about OpenFlow, but this is where OpenFlow doesn't work, really. You cannot have session to every device and program forwarding tables. You leave it to distributed protocols and local behaviors. So myself and Russ White, we often use this slide in our presentations, but the truth is policies don't belong to protocols. If you want to do any policy, you decouple it from reachability, you have centralized entity that has complete view of the network to enforce, to compute the policy. And this is what PCE does, really. Northbound, it takes constraints, business logic. Southbound, it spits out path topology, right? And as we said, at some point, centralized model just breaks. You cannot have a centralized brain configuring everything. You need to provide right level of abstraction for different levels to scale. And routing is not a bad database. So CAP theorem tells us we can always choose to, even though there are different opinions about this, but practically you could be either available, consistent partitionable, or available partitionable. You can't have all three. Since networks are eventually consistent, so after convergence, there's consistency. We can use them. They're good enough because they're eventually consistent. They're always available after convergence, and after you partition network, it still works. So it's actually pretty good as a database for network to be distributed, if you look at network of distributed system. And this leads us to you centralize logically, but distribute physically. And keep things simple. So, Nick, I love your opinions here.
Yeah, I mean, this is the thing that, in my opinion, makes it, keeping the logic central to a set of controllers, right? So you can make the controllers redundant geographically and network-wise. As long as they can synchronize between each other. That's the thing you have to worry about, is keeping that synchronization of a redundant controller system up to date. But then keeping all of the logic pushed down into the physically distributed equipment is, it's a model that works. And I like to think about explaining it simply, like a lot of the controllers will allow you to sort of just go and get a glance of what's happening. And it's generally pretty easy to consume by the nature of what the controllers are. And there's a bunch of different options from they're all, they all perform the same things because they all have the same underlying protocols.
That's actually something I'd like to explore just a little bit more, is the controller piece. And so, we've talked a lot about the edge devices and the capability of the fundamental protocol, but a lot of this is driven by the idea of building a label or building that stack, right, from a controller somewhere. So, what does the market look like today? What's out there? What are the controllers that people are using? And then, what is available if we wanted to play and toy around with this for us mere humans who aren't running networks that do this? all the time to get some experience, having a controller-based SR network?
So there's, I've spent a lot of time on this. There's a handful of commercial options out there from, all of the major vendors have one. And from the open source space, the one that I've seen the most use of is actually Open Daylight. Yeah. And there's some quirks in using Open Daylight. Like if you want, the topological view and things like that, there's some extra work you have to do. But it's the one that you can actually get. You can lab it up today if you have the VMs that support segment routing from the network appliance perspective. And those are pretty much universally available from the vendors that do segment routing. You can get that, spin it up in your environment of choice, and you can either connect an external PC to it, or you can run the VM internal to the virtualization system, and you can make all of this work. I've got a handful of GitHub repos that are essentially canned configs for a bunch of the major vendors. All you have to do is plug in your PC and have the VMs to run. You can mix and match them. I've done multi-vendor testing that way as well. But the PC is really the secret sauce, like you were sort of alluding to, Jordan. It's the thing that there isn't a lot of talk about it, to be honest. But it's definitely the thing that makes this sing.
And are the vendor implementations of these, they're from the majors, right? You kept mentioning the same list of 3 majors. I'm sure there's possibly more. But the idea for these vendor implementations, are they the controllers vendor specific? As in,
no.
if you go to Cisco today and you get a Cisco controller, or is it more interoperable? That Cisco makes a controller, you're going to pay for that controller, but that controller is going to be able to run an SR network across the board. I'm just picking on Cisco because, Cisco's the 800-pound gorilla, right?
Yeah, so I've been going to test stuff for 10 years to INTC to Berlin, and I stopped probably when I left Ericsson, but even back then, we tested PCs from different vendors and fixed most of the bugs. So I'm still following through what's being tested every year. It's also being presented at MPLS Congress in Paris. So at least Nokia, Juniper, and Cisco PCs have been tested multi-vendor environment. I believe Huawei as well, and they're all working. The BGPLS implementations are really stable by now. It wasn't the case 5 years ago. It was pretty horrible, actually. PSEP implementations are being stable for at least 2 years. So you might see some secret sauce, as Nick said, on PC level. How do you compute PCs in the best way? How do you apply better logic? How do you recompute paths? How do you apply machine learning on top? All this stuff. What kind of data can you take northbound? Can you take, cost of the fiber between 2 and 4? As part of the computational logic. But it's really more towards business logic than basic functionality. Technically, stuff is working.
Right. So really, if you're making a decision between vendor implementations, you're looking feature to feature. Like, does it deliver, does it deliver you the ability to build the logic that you want to into the network? It's less about what's the underlying gear you're running. It's more about, does this controller meet my needs? And I'd be curious, and I don't know if you guys know this, but is there a prevailing winner in this market already? You know what I'm saying? Like in some markets, some people step out and say, hey, this controller seems to be that everyone's gravitating towards, or is it just everyone's kind of finding their way and doing some different stuff right now?
I think it's still early, but to take a step back, the thing that's really nice about it, and the reason that it works the way Jeff described, is that the southbound is largely all the same. From the controller to the equipment, you have, connectivity that's going to give you link state, right? That's going to be probably one of 2 things, right? It's going to be a standard protocol. Yeah, there you go. And then you've got, your mechanism for pushing your policy, which is typically going to be PSEP, but there are other options out there as well that are also standard. So that's the thing that makes it, in my opinion, the ability to have it so wide open to whatever you put in there. Is that southbound interface is largely available and standard and just kind of well-traveled and battle-tested.
Yeah, so from what I see, and I spent a year with Nuash building a lot of this stuff, it's not only kind of core logic of PCs to compute the path. It's really ability to talk to SD1 controller, ability to talk to cloud controller. So while I was at Nuash, we actually built a combination of cloud controller and one controller to build end-to-end paths between data centers. So there's a lot of interworking and interactions between these two. And you start looking into how good are APIs exposed, how good is the validation part. So there's much more, again, it's more towards business logic and overall implementation than just doing path computation. I would say path computation is a given, any controller can compute a path. Doing it in combination with someone else is much more complex. Reporting capabilities are complex. Combination with optical controllers, combination with radio controllers, all the stuff is finally coming here, right? Because someone has to compute a path in your MPLS network. But does it interwork with optical controllers, which is completely different logic? How does it interact with business logic? I think this becomes much more important than just basic technology here.
So I want to also call out Nick here a bit. Nick, you've been doing a lot of this practically. What are there any hurdles that you've hit in your implementations or in your testing that we haven't really talked about here? Is there something that, like, if someone was going to get started, you can say, hey, look out for that. That's a pit of despair. Avoid that thing, because that's gonna be painful. Or has we kind of hit those items as we've gone along here?
The biggest one I found is that I mentioned earlier, because of the things that I needed to do, complex traffic engineering, right? I found that the label stack not matching, just making sure that worked, was the thing that I had to really kind of figure out. And it wasn't just me. There were, my colleagues and stuff were also working on this as well. Just to make sure that all of that stuff matched up to be able to do the things that we wanted to do. That was probably the biggest hurdle. There's, for the most part, it's well documented across the board on how to make this work, on, your vendor of choice, and the amount of data that you can consume on this is there. The one thing that doesn't really exist is if you want to start doing complicated things with controllers, there isn't that much out there, because I think, again, it's still early. So I think that, the more people that are, spinning up whatever they can to do their, complicated, traffic engineering and topological traffic movement, that if they could write it up, get socialize what they find, I think that'll be pretty big. But for the most part, there wasn't any huge gotchas out there. This seems to be very well put together, and implementations are pretty complete.
So if you find this interesting, you want to contribute, FRR, free-range routing, is actually going through PC implementation as we speak. The segment routing implementation has been contributed by Orange. So there's at least ISIS implementation and OSPF, I believe.
Yeah, Orange contributed the OSPF, I think. And then the ISIS is fairly new, the ISIS-SR.
Yeah, this was this German guy who called it. I don't remember his name. But anyway, segment routing is already there. Get involved. It's open source. The discussion is really interesting. And, there are more and more people who want to use it. In service provider space, you see, again, Orange very active. You see VMware. You see some people who are willing to put people, money, and make it really work. So it's the right time to get on board, contribute, because now you can actually influence how things are done. And this is a beautiful moment in life.
Yeah, for sure. And this, it's not just a service provider tech, right? I mean, I know plenty of big campuses that run MPLS cores that would very much benefit from being able to sort of explicitly move their traffic in ways and set up TILFA, FRR, and things like that for their redundancy. Basically, that's what topology independent, loop free
alternative.
Yeah, to run it. Basically, it's a redundant path. To put it in extremely crude terms, but you could definitely benefit from this in any large environment that wants to simplify and maybe have a little bit more visibility into the things that they're doing.
So Jeff, you mentioned the fact that, this is fairly mainstream from a standardizations perspective. It's been implemented, across multiple vendors. Is there anything that's coming from a standards perspective, or are we kind of like reached the state where segment routing is just ready to go and we're just going to leave it alone and focus on other things right now?
So core functionality is ready, implemented, and tested. And it's been shipping for 3-4 years. So what's coming are really interesting extensions. So remember, we removed all the states. So suddenly multicast doesn't work. You cannot do RPF anymore. So there's a lot of discussion about how do we do multicast? How do we replicate traffic? You could think of beer. You could think of some pretty static provisioning. So there was, I'm not going to call it names, but it was called, what is it called, 3-seed. So actually you are programming a seed from central controllers that said replicate to A, B, and C, which looks like OpenFlow. And, I'm not big on this kind of solution. But so there's some multicast stuff, obviously. There's a lot of work on making network more complex. So I would argue if you have good controller, why would you need to do any of this? But I seem to be in minority here. So a lot of people are very excited about having different computational algorithms distributed. So so-called flex algo. What it gives you is that your router could not only compute Dijkstra, but maybe Steiner and some other algorithm, cheapest path, and assign different labels to different topologies. So in this case, your network itself can build paths based on business logic. For example, in this network, I want path to be the shortest one. Here, I want it to be, the cheapest one. So there's a significant amount of development in this area. Again, from my perspective, if you have controller, single topology is just good enough because controller can compute all the stuff on behalf. But some people want to do it distributed. So there's a lot of work in this area. I would say a lot of work these days goes into network slicing. So how do you combine segment routing with radio, with dedicated resources? How do you have all the things that are vertically integrated doing same thing? So this is where most of the work is happening today. From IGP perspective, there's some minor stuff. So as you know, about 6-7 years ago, we started moving signaling of objective functions into ISPF and ICS. They were called, what do you call them? Extended attributes or so. So now we can signal on IGPs, delays, variation, bandwidth, all kind of stuff that then goes into BGPLS and to the controller. So there's a bit of this work to get more data to the controller without having management session to the controller, but distributing through IGP and then having BGPLS signaling to the controller. Because when you build your graph, you want to know as much data as you can about state of links and all the attributes associated with it, being delay, being bandwidth available, being maximum bandwidth block allocation available, all this kind of stuff. So there are small extensions to IGPs and BGPLS to signal the spaces.
Very cool.
Yeah, from what I've seen, Flex Algo is the sort of new hotness. And then, from the operational point of view, it's just like any other sort of emerging technology where it gets refined, across the board. You get better OAM support. You get, features like SBFD added in, basically BFD that runs inside an LSP that allows for faster failover, things like that. Like the more complicated protocols, that tend to either center around, usability, like troubleshooting stuff, or redundancy. Those things are sort of getting a little more refined and distributed across different platforms, is what I've seen. From the protocol perspective, Jeff, obviously.
So another interesting use case, and actually very separate from what you see here, is Egress engineering. All public clouds use it today. So this was kind of major push, and very few people know that Juniper would support this years ago on RSVP. It became really this cool new hot technology with segment routing. So what you could do here, on every BGP session, you could assign a label, adjacent seat in a way, right? So in this case, you don't need to run best pass on the egress node. You just follow your adjacency seat and you advertise them. You could send it to a group of peers, single peer, so you can define the logic. So in this case, your centralized logic can decide, I want you to exit towards peer B versus peer A. While from BGP perspective, maybe peer A is preferred one. By using segment routing, you assign the adjacency seat, you signal it through BGP left to the controller pushes it down, then when you reach egress node, you look up adjacency seat, you go to peer B. So again, used by every hyperscaler today. Pretty cool technology.
I think the integration with like OAM is really interesting to me, because you could, depending on how advanced your controller is, just logically, I mean, you could build all sorts of really cool active monitoring of an LSP, or whatever it's called, an SR, I guess. But, monitor all of the potential LSPs on your graph or whatever, and then choose it based off of some metric that you care about, like, whether it's bandwidth, or if you're like HFT and you love low latency, you could test all of the paths real time using OAM and then actually move stuff around. That's interesting to me.
I think you can largely do most of that with the, with what's available now. It may not be quite as fluid as you described, but for the most part, your PC will know, latency and bandwidth statistics on your links, and it understands, how many hops to this and that. So all of those bits are there, and you can optimize LSPs based on those attributes now, latency and hop count and things like that.
There's even some built-in stuff you wouldn't even have to home grow a lot of that, even depending.
Yeah, so if you look at Deutsche Telekom specifically, they actually built complete testing machinery based on segment routing, because now you can identify every hop and how the OAM packets come back to you, right? Because it's in the path. So there's actually a document describing how they do it. I can share it later on. It's pretty interesting, and you couldn't do it with LDP because it's shortest path based, so you don't actually know. You couldn't use RSVP because it would require state per tunnel in the network. With segment routing, there's no state. You just identify the path you want to follow and measure, and you do it at any ingress to any egress. So it's really powerful paradigm.
So I have a quick question. Is there any efforts to map diffserv into SR? Because I understand that they had LDP stitching with the mapping servers. But what about if you have a IP traffic classifier in the header of the IP packet? Could you map that to a specific path with SR?
Oh, yeah,
or is that
absolutely.
being done?
So for whatever reason, it was called policies. I still hate this name, and steering into the policy, which I hate even more. But what it is really, it's binding of FAC to tunnel, right? So if your FAC happens to be DCP value, so be it, you just look it up and you switch into a particular tunnel. Another way, kind of naive way of implementing virtualization, is to have a label space or just a loopback per virtual topology. So you say, I will have topology with traffic that marked with DCP 46. In this case, you could have a bunch of loops that are allocated across your network that will only use label space associated with this topology. This is what FlexAlgo is actually doing. Because now you can say, my topology with FlexAlgo 4 is going to be based on diffserv. That's exactly the use case. But practically, from ingress node perspective, what you need to say, look up particular attribute of a route. It's not necessarily destination anymore. Could be anything. Could be, again, diffserv value and switching to particular tunnel. And probably not for this discussion, but there's some work in BGP, which is really cool. Now you can signal from Egress node which tunnel it wants you to take, and we call it a coloring. So you've got an attribute in BGP update saying, I want you to take tunnel of color A or color B. So Egress signals to Ingress, I want you to reach me through tunnels that meet these particular characteristics, which again could be diffserv, for example. So let's take a look at how the stuff is really working from controller perspective. So you've got your network here. You run an IGP. So BGPLS, as Nick said, really container to transport IGP data to somewhere else. So on one or two nodes, you'll have redistribution of IGP into BGPLS. And as we said, as of today, we can signal most of objective functions in network through IGPs, being bandwidth, delay, latency, availability, whatnot. So all this stuff is going to the controller and becomes part of your networking graph as attribute. So now when you get a request, I want a path that meets particular constraints in terms of bandwidth, delay, you could go and run basic CSPF, prune all the paths that don't meet it and compute ones that does. So this is how topology acquisition is done in modern network. From provisioning perspective, again, I'm using Open Daylight here because it's very visual and it's really done in right ways where you decouple kind of your computational logic from instantiation. So you want to use PSEP, it's here. You want to use I2RS or OpenFlow, it's still there, right? You just subscribe particular data. So after you have computed the path, it becomes an operational. You use PSEP to the head end, and you provision the path as well as how you bind particular FEC to this path. Could be done statically. You could say static route to destination 10, take this tunnel, and tunnel has unique identity. You could use, as we said, BGP coloring, and now Egress will signal here, if you want to reach me, please use tunnel red. Tunnel red is going to be provisioned from the controller, and when destination is this guy, it will use this tunnel. So it's kind of combination of distributed signaling and centralized provisioning. PC could be local. So for many years, Open Daylight didn't have PC. It only had PC logic to provide this transport to controller outside. I think this is how Cisco wanted it to be back then. Now there's a PC. I've never touched it. I know Nick tested it, and probably this is something you could get and start playing with today.
Yeah, it's available out there. Now, in full disclosure, I did not actually do the majority of that work. That was some researchers on our team. But I did look over the things that they completed, and it does what it operates as a PC. So it's definitely usable and available right now.
So this was the last project I was involved in a deal before I left Ericsson, actually building full multi-layer stuff. So not only segment routing and transport, but attaching VPNs to it, attaching optical stuff. I'm not sure where it is today. So the Young model for segment routing is done. It's going to be last call probably today, tomorrow. So you could completely use it to fully configure segment routing and get all the operational data. The OpenConfig one is in pretty good state as well. This is what we were envisioning in Open Daylight. Again, I'm not sure where it is today, but back then the idea was to provision everything from ODL, and it looked really great. So just to explain you how stuff could look in SDN environment. So through BGPLS, we've acquired our topology. We know exactly. So in this case, we use bandwidth as a metric, right? So we know all the bandwidth available on every link. When we get a request, I want a path. We already have the graph. We run CSPF. We see which path can be computed. So the logic is going to be, I want a path that minimum bandwidth of 10 gig and maximum delay of 10 milliseconds. So since we have all the attributes here, we prune all the paths that don't meet it. We choose one path that does meet it, which becomes path A to F through B. Actually, through E, sorry. So path instantiated, you push it through PSEP, you hit the traffic towards F, it will take this path. So as simple as it is. This is pretty much how logic works, and combination of BGPLS northbound and PSEP southbound. So more interesting use cases, and why is it good to see all of the network rather than just what you see? Why is it good to have PC centralized, logically centralized, rather than running on a P router? So in this case, request is 15 gig. If you look at any of the links available, actually, if it's just view of router A, it cannot provide the path because none of it is more than 15 gig, right? However, since centralized view is there, and we know that if we distribute traffic across these two, and segment routing gives us this ability, because now you can configure weights. And in this case, if I distribute traffic reasonably evenly, I can still provide the service. So now I can actually provide service associated with two different tunnels, configure load sharing locally, and provide service which I couldn't provide before. So this is kind of on the service availability perspective. So again, we provision it. And the forwarding action is to load share across B and C, simple as it is. So load sharing is going to be per flow, even if there's some fat flows on one side, mouse flows on another, it would still probably be around 60-40, which is good enough. Feedback. So now with centralized controller, we are getting data finally that's near real time. Streaming telemetry is there pretty much on every platform today. Gives the ability to quickly recompute the path, reoptimize, provision another one. We could do this versus VPT as well before. This is much simpler, doesn't require any resignaling. You just provision secondary path on the head-on router, and then in make before break fashion, you switch over. So it's not as painful as it used to be with RSVP, with all the resignaling, tearing down, instantiation, this kind of stuff. What else? So it's integration of optical and packet domains. We discussed it before. In real use case, we built it actually. So by binding CT, you can identify optical path on the device that has both optical notion as well as packet notion, and gives the ability to choose right path in both domains based on single logic, which is segment routing label. Nick, are you doing something like that in your network?
Not currently. That is an area of exploration that I want to look at in the next probably 24 months. Because, on our network, we've just deployed a new optical substrate. Well, we're in the process of deploying it nationally. So it's an open line system. So, there's some more options that can be leveraged. And I do want to look at that, but we currently have not done any work on that.
So the idea is that you've got So usually there are separate PCs, one for layer 0 to layer 2, or actually layer 1, and one for MPLS. And they need to cooperate. And in OpenDelight, again, idea was that you've got this message bus called model-driven cell, where you could subscribe to particular events and you would share data and build paths that's kind of vertically integrated, but end-to-end.
Yeah, it's definitely an area of interest.
So this is something that's really interesting. So today, you want to be able to signal your path in one single point, right? You have one people, you have DC people, you have some other people in between. So while your business logic is pretty much dictated by the company policy, right? Even so you're in different silos, the way you monetize your services is the same. So as we said, not everybody, actually very few people run MPLS in data centers today. So a number of reasons. Data center people in general are afraid of MPLS. You cannot allocate labels through ZTP. So DHCP doesn't provide label today. We tried to do LARP, which was label ARP, but didn't go anywhere. So anyway, data centers today are IP. So what do? You've got the controllers that can go and provision label stack here. However, you cannot use label stack in the data center because it's IP. IP is the technology. We know it's VXLAN today. It's probably Geneve VXLAN GP tomorrow. It's still IP UDP. So there's whole frameworks called SR over IP, which is an RFC by now, based on MPLS in UDP. In this case, we encapsulate SR stack or MPLS stack in IP UDP and replace destination IP address by destination IP address that your next label in the stack is resolved to. So in this case, it's DC gateway. This device understands both segment routing and IP. So how does it know it's segment routing? There's dedicated port IANA allocated that says, if you see this port in my UDP packet, it's MPLS. So it pops IP UDP, and next label is actually binding seed that identifies this tunnel. So it looks up binding seed, sees the tunnel it needs to take, going to take this tunnel. Since destination VM is here, it's going again to encapsulate traffic in IP UDP, so VXLAN, and send it here. So this really requires two things. One is integration between one controller and data center controller. Another one is ability to push label stacks down to the VM. And this is pretty much it. Your fabric is completely agnostic to presence of SR. It's IP UDP, it's VXLAN. So it gives you end-to-end picture. Actually, we wrote a draft called NFIX. Nokia has implemented this technology. It's being sold today. It's going to be presented Common ATF during Crouching Working Group meeting. Just take a look. I think it's really, really elegant technology. And if you want to do something like that today, you can do it. Every vendor, every silicon supports MPLS and UDP today. Kernel supports MPLS and UDP. So you can just do it. And you don't need the Service 6 or any other stuff that's, it's still kind of futuristic. So a few words, that's exactly what you see here. You encapsulate your seed stack in IP UDP, and your destination IP address becomes just next thing in the SAR stack. And guess what? You can also use UDP entropy to load share traffic in your IP fabric in data center. So there's implementation. It's supported in every silicon. I think it's a really good solution. So if you would ask me, should I do Service 6 or this? Because, again, it could be UDP over IPv6. It doesn't really matter. I would definitely say this works today. Just works. So I think we are pretty much at the end of presentation.
All right, good deal. So before we cut it off here, I'm just going to leave a couple seconds of silence and see if there's any other questions before we jump off the recording.
Sorry if this was already asked or answered or spoken about. I know we talked about label depth and like scaling of that a bit, which I know Jay knows a lot about. However, what about like scaling of the LFIB? Is there any like concerns there? Because it seems to me like you would end up having a lot more labels than usual, but I still don't quite understand it all. So do you have to worry about like having just a ton of labels in your network and actually run into scaling issues there?
So the answer, it depends. So if you're just doing single nodal seed per device and then adjacent seeds per interfaces, you should be okay. It's no different than, I mean, it is more than LDP because LDP did syncing. Here, they're all unique labels, but you're still okay. When you start doing label space per class of service or per algo, suddenly you're multiplying all of this stuff. And this is where it becomes really concerning. As I remember early days, Huawei proposed to build like virtualization layer by assigning additional loopback to every new class. So you end up with millions of labels and you're pretty much done, right? So on high-end silicon, something like Juniper 3 or FP4, whatever Cisco is using these days, you can actually look up one label in the context of another one, which gives you indirection. But practically, you would like to look up label and know what it is, not to go and look up yet another label because the cost associated is reasonably high. So you want to keep it under control, really. And if you look into merchant silicon, Jericho scales reasonably okay to probably, I don't know, today, 500,000 labels or so, maybe higher. DNX or something you would run in a data center, you're in, 20, 30, 40K.
So practically speaking, I have not run into that, Chris.
Cool, thanks.
So how many labels do you have today instantiated in your LFIPs?
I don't even know. I'd have to go look. It's not an obnoxious amount. It's nothing that we've had to really even think about.
But kind of to add, the only labels that instantiated in the LFIP are nodal seeds. The adjacency seeds aren't. They're only instantiated on the node that allocates them. So it gives you kind of ability to scale much more.
Okay. Well, I think this is a good place to wrap it up then. So, Jeff and Nick, thank you so much for putting this together and sharing both your deep level knowledge of the history and kind of how this all came to be, as well as practical side of experience in implementing some of this technology. I know I learned a lot. I hope everyone else did as well. And I think that's it. So thanks again for those who were able to join us here in real time. And hopefully we'll do this again real soon.